The next one is a very fundamental one, especially for you to define recursion on trees later. So pay attention to the next one. So the tree formed by descendants of n. So we are talking about there might be trees inside a tree. So that's more like a recursive concept over here, right? So it's called the subtree rooted at a particular n. And the n over here, again, can be replaced by any of the nodes in the tree, right? Let me talk about this concept right away. And it will be the best explained if I draw some diagram over here, right? So start from the biggest one, right? You can think about, let me use this one over here, okay? You can think about this one here. This part over here, the entire tree over here, this one here, okay? So entire tree over here is called the subtree, rooted at David. And because David happens to be the root of the tree, so this particular special subtree is going to be just the entire tree. So this is also a subtree, right? A subtree can just be as big as the original tree. It's pretty much like when we talk about an array, a subarray can just be maybe this big, or it can be this big, or it can be this big, or it can be just the entire array. Similar idea. So subtree is like a subarray. Okay, so think about the subtree over here, analogous to, right? Analogous to the sublist or subarray. Similar idea, right? Let's think more. Okay, and what about, let's give another example over here. What will be the next subtree that'll be the biggest? Well, it turns out over here, let me just try to draw that over here. So how about this one here? So quiz actually is going to be contain all the descendants of quiz, right? This pink one over here, which is going to contain quiz, Elsa, Anna, Shirley, Vanessa, and Peter, right? This one over here. So this will be the subtree rooted at quiz. Subtree rooted at quiz. Right, let's see one more. Okay, but you can pretty much get an idea. So we can talk about a subtree rooted at a particular node, and that root can be either of the nodes in the tree. It can be, right? What about the smallest subtree in this particular tree? The smallest subtree will be simply the root itself. So for example, let's say this one over here. How about blue? You can think about Vanessa over here is just a subtree over here. Subtree rooted at Vanessa. Right? So very naturally, let me ask you the following question just to conclude the demonstration over here. How many subtrees of this particular family tree? How many? And you want to think about this in a more general sense. Given any arbitrary tree to you, if I might just ask you about how many subtrees there are in that particular tree, you can pause the video and tell me the number. Alrighty, assuming I thought about it, well, without telling you the answer right away, the way to calculate how many subtrees, all you gotta do is just to count the number of nodes, because each node can be the root of a particular subtree. In that case, there can be one subtree rooted at David, one subtree here, rooted at here, one subtree rooted at here, one subtree, 1, 1, and 1. 1, 2, 3, 4, 5, 6, 7, 8. In this particular case, it's going to be 8. Right, sorry. Let me just cancel that. Okay. 8 in our case. But just going to be the number of nodes. The number of nodes in the tree is going to correspond to the number of subtrees in that particular tree. Alrighty, let's now move on to the next concept. And the nodes with no children. Well, in that case, it's called external nodes. Let me talk about two at one go, and then I'll illustrate to you. Okay, and also we talk about also the nodes with at least one child. It's called internal nodes. So here we have the notion between internal versus external. All right, let's now move on. We'll move back. I'm just going a little bit faster in the bullet points presentation. You can definitely read the definition more carefully yourself. I thought it might be more worthwhile spending the time visualizing for you. So now we're talking about external nodes, actually, let's say we talk about internal nodes versus external nodes over here. Right? Very easy to see. Okay. External nodes are all not necessarily at the bottom. Think about all the nodes without any children. So that will be Shirley over here without any children, and also Vanessa without any children, and also Vanessa without any children, and also Peter without any children over here, and also Anna without any children. Right? You can see the external nodes are not necessarily at the bottom of the tree. You can see Anna being an external node is not really at the bottom per se. Right? Let me just make that notes over here. External nodes not necessarily at the bottom. At the bottom level of the tree. It might be, but it may be not, right? Not necessarily. Do we have any more external nodes? Well, you have spotted that, Ernesto. So these are all the external nodes in which they simply don't have any children. And the rest will be internal nodes. They do not overlap. You can see Chris, let's say for example, Chris has 2 children, Elsa and Anna. Elsa has 2 children. In that case, it would be Shirley, Vanessa, and Peter. And David also has 2 children. In that case, it would be Ernesto and Chris, right? Right? You can see internal nodes will be David, Chris, and Elsa. So we got 3. Right? I can write it down over here. For our example, we got 3. And for external nodes without any children, we got 1, 2, 3, 4, and 5. We got 5 of them. Right? Very important concept over here. And later on, when we actually talk about the mathematical property, we'll actually try to bound the number of external nodes versus internal nodes. And also, we will want to prove some property between the number of external nodes versus internal nodes as well. But we'll get there later. Alrighty, let's now move on to the next one. And the next one will be about, I think, a series of concepts over here. Let me talk about one thing is about edge, the edge of a tree. Whenever you talk about a pair of parents and child nodes, that will be an edge. Well, visually, it simply just corresponds to, let me just say, an edge, right? For example, there is an edge between Ernesto and David over here, right? This is an edge. Very easy concept. Right? The edge will simply connect the child and also the parents, right? And there's another one over here. And you can see more examples over here. I'll let you see them from the slides. And a sequence of nodes where any 2 consecutive nodes form an edge is something called a path of the tree. For example, let's see this. Let's consider the following path. Let me use the pink just to try to include several edges at the same time. So let's say from Vanessa to Elsa, Elsa to Chris, and also Chris to David. So this is actually a path, and it's a very special path. It's called the ancestor path for Vanessa. So this one here is called the ancestor path of Vanessa. We kind of start from Vanessa and we keep going to the parents, and the parents all the way up to the root, including the root, and also including the initiating node itself. It's called the ancestor path of Vanessa. Of course, all the nodes involved in this particular path are the ancestor for that particular node, which we went over already, right? That's really the path. Of course, ancestor path is just a special path. You can also have other paths which may not be this long. For example, you can think about this will be just another path with 2 edges. That's also fine. All right. All right, and then we're going to talk about 2 important concepts which we're going to implement in Java later, right? So think about as we go over about these the definition for these 2 notions. Think about how you may implement that recursively in Java, which we're going to go over, but it may not hurt for you to think ahead, right? The first one is about the number of edges from the root to that particular node n over here, right? Let's do one at a time. It's called the depth of n. All right. Let's now apply this definition and do that right away. Just remember definition again. The number of edges from the root to n, right? So it's called the depth. So for the depth, let me just highlight it. Depth over here. The number of nodes. Sorry, number of edges from the root, right? And of course, every node in the tree can be calculated for its depth. So let me just try to fill in the depth for every node just for completeness. Right? For every node, I'm going to say d is equal to d is equal to d is equal to d is equal to d, and also d over here. Right? Let's start from the minimum. By definition, there is simply no edge to go from the root to itself. So that's why, by definition, the depth for the node the root will be just 0. It's a special case, right? Don't forget, this is the root. The root of the tree always has the depth 0 by definition. What about these two nodes? You can see these two nodes, we say that they are actually at level 1 because they both have depth 1. There's only one edge to go from the root to that particular node. Go from the root to that particular node. So the depth will just be 1. Right? Oh, I forgot about Anna over here. Right? So what about Elsa and Anna over here? Right? In that case, you can see they're at the same level because for their depth, for Elsa, we got 1 and 2 edges from the root into Elsa. For Anna, we also got 2 edges from here and to here, right? So that's why it's 2. Finally, for Shirley, Vanessa, and Peter, for Shirley, it should be depth 3. From the root, 1, 2, and 3. And for Vanessa, 1, 2, and 3. And for Peter, 1, 2, and 3. Right? So all of them will be simply 3. Right? So the idea about depth is actually pretty simple visually, but you should really know how to compute it automatically using some recursive algorithm, which you can think ahead about how to do it, but we're going to talk about it in the later part for the lecture. All right. The next one is related to the idea about depth, which is about heights of the tree. By definition, the height of a tree will be the maximum depth among all the nodes, including the root of the tree itself. Right? So that will be the definition for height of the tree. And let me emphasize, the tree over here may not necessarily only refer to the entire tree that's rooted at the root. It could be maybe the height of the subtree rooted at maybe Quiz, or it could be the height of the subtree rooted at Vanessa, and etc. So you can definitely calculate the heights for any arbitrary nodes, meaning that we want to calculate the subtree heights specifically. Let's see some visual example together. Okay, so we are not talking about the heights over here. Let me highlight. So the height is what we are concerning about, and let's put down the quick definition. So this will be the maximum depth among all the nodes under that particular tree or subtree root. Right? The easiest one, which we already got all the preparation work done already, right? Let's take a look at what will be the heights for the tree rooted at David over here. Right? In that case, the height will be basically find out the maximum depth. Visually, we can see the minimum is really the minimum depth is really the root itself. You can see the depth as we calculate it is simply 0. And as we go deeper, you can see in this case, the bottom level over here has a maximum depth, in which case the maximum will be just 3. Right? Let me write down the first one over here. In this case, the height will be equal to 3. However, I want to emphasize this one here, and then I'll do another example just to show to you. Okay, so the height over here is really the height of the subtree rooted at David. Right, so that's really important to see. Right, let me do 2 more examples, shall we? Let's do 2 more. The first one. What about, let's say we choose this external nodes over here. What would be its heights? Over here, right? You might be thinking, should the height be simply the maximum depth, which would be 3? That'll be wrong, because the depth over here that we calculated was relative to the root, David, right? 1, 2, and 3. However, when you're now focusing on the heights for the subtree rooted at this particular node, the depth value will not be 3 anymore. It should be recalculated, right? In this case, what you will do is you're simply just going to say, for Vanessa over here, the depth over here would just be 0, right? So this will be relative to the subtree root, which is Vanessa. And given that Vanessa actually has no children over here, In that case, we simply don't, we cannot really get their depth to really compare. So what's the maximum depth over here? In that case, it will just be 0, right? So it's really important to say that as far as this particular subtree is concerned, that's rooted at Vanessa, the height will be equal to 0, right? So this will be the heights of subtree rooted at external nodes. Let me emphasize that. That's why I want to do this one first. External nodes, Vanessa. Meaning that it will be the same for every other external node in the tree. If I want to calculate the height of the subtree rooted at Peter, rooted at Anna, rooted at Ernesto, rooted at Shirley, they will the heights will all be 0. Right? Let me write it down over here. It's a very important conclusion that observation we can make. Right? Over here. So heights of subtrees rooted at external nodes are simply just 0, because in that case you only got the node itself, in which case its depth relative to itself will just be 0. So that's why the maximum depth will just be 0 by definition. Right? It's a very important mini conclusion that we are reaching over here. Right? 0. And we talk about external nodes over here. External. Right? Let's do one more example for the heights. Okay? Why don't we choose, let's say, quiz over here? Why don't we choose that one there? Let me maybe use, actually purple is okay. Actually, let me use a different color. How about red? Okay, let's say quiz over here. What will be the heights for this particular node over here? Right, the heights. And I'm going to use the color red to really fill in the depth of all the nodes under this particular subtree, right? For quiz being the root, the depth will just be 0, right? And the first level will be Elsa and Anna. In that case, depth will be just 1. And for and then under and then the next level will be Shirley, Vanessa, and Peter. The depth will just be 3. Oh, sorry, 2. And the depth will be 2, and the depth will be 2, right? And I really meant to really write these two together just to show to you, whenever you talk about the depth, you should really know about which root are you is your calculation relative to. In this case, Elsa over here, if you're calculating its depth relative to this particular root, which will be in blue, David, it will be 1 and 2. So that's why it's 2 over here. On the other hand, if you want to calculate the depth of Elsa over here relative to quiz being the root of the subtree, it will be only one edge. So that's why it's 1. Right? It's exactly why I'm writing these two down. Right? Let me just highlight them over here. You should really be very careful about, okay, over here. Okay, so here, different depth with respect to different roots. Okay, for this one, it's actually David, and for this one, it's actually quiz. All right, and what will be the maximum depth of the subtree rooted at quiz? The maximum seems to be the red one, which should be just 2, right? So the height will just be 2. So the height will just be the maximum, which will be 2. All right. Right. So the calculation for depth is really fundamental, which will impact about how you actually calculate the heights, right? So the visual example is not too difficult to understand. You just need to know exactly the context, and you can also think about exactly how you may calculate these two. How you may actually implement these two computations recursively. It's very natural to really define these two notions recursively in Java. That's something we'll talk about a little bit later. All right. Alrighty, so that's about all the terminology I would like to speak about the general tricks. And let's now move on. Before I move on, you can see just more example about calculating the depth over here. Of course, you can see the depth over here is relative to the root of the tree over here. But just remember, when you calculate depth, it should be relative to some certain root, which may be any arbitrary node in the tree. It depends.